Hi everyone, welcome to our poster on self-supervised denoising titled Self-Supervised Denoising Transformer with Gaussian Process. This is a joint work with my colleagues Jeya Maria Jose and my advisor Vishal Patel at Johns Hopkins University. When we consider deep learning based denoising methods, they can be broadly categorized into supervised methods, unsupervised methods, where supervised methods requires noisy image and its corresponding clean image to train the network weights and perform the denoising task. Recently, there is a well-known technique where we don't require any clean image. Instead, we can take two pairs of noisy images and train the network weights. This was proposed by the work noise to noise. Recently, there are self-supervised methods that are developed to train the network weights using just a single noisy image. Here, we are trying to address this problem of self-supervised denoising, which requires only single noisy image to train the network. Limitations of the approaches like noise to noise is that it is practically difficult to obtain pair of noisy images with the same clean background. On the other hand, limitations of recently proposed Hong et al. Is that they use a naive regularizer that accounts for the difference in the clean background images, which might produce errors in the pseudo-ground truth noisy image. Here in this slide, we explain the reason behind generating pseudo-ground truth using Gaussian processes. Let us consider two independent noisy images Y and Z, which has almost similar background, background image X, such that expectation of Y given X is X, expectation of Z given X is X plus epsilon, where this difference epsilon can be formulated using a Gaussian distribution as shown here. This allows us to formulate a joint Gaussian distribution between Y and Z noisy images as shown here. If we consider f is a function that performs denoising task, we can formulate the joint Gaussian distribution between the functions f of y and f of z as shown here. If we know the mean image mu z, then we can predict the mean denoised image for y using the Gaussian process as shown here. As explained in the previous slide, we can extend this to multiple noisy images with almost similar background. In order to achieve that, given an input image y, we downsample the input image and cyclically shift it as shown here, and their corresponding function mappings of denoising task are f1, f2, f3 as shown here. So the function denoising mapping can be formulated as like here. Given n downsampled images and their corresponding function mappings, we formulate a joint Gaussian distribution between these denoising function mappings as shown here, where the mu can be computed with a closed form expression as shown here with a covariance matrix K as shown here. We can use this mean prediction for the given downsampled image and use this as a pseudo-ground truth generated by the Gaussian process. Ultimately, we can do supervision using this pseudo-ground truths generated from the Gaussian process and the network's prediction X spread, and update the network weights in order to learn the network weights to perform the denoising task. The following diagram shows the overview of our proposed Gaussian process denoising method, where we take the input image and downsample and randomly cyclically shift to obtain the downsampled images and pass them to the denoising transformer, and also use the Gaussian process to generate the pseudo-ground truth for each uh, downsampled image and compute the loss between the network's prediction and the pseudo-ground truth generated from the Gaussian process to update the network weights in order to learn the weights for denoising task. Following diagram shows the baseline network used to perform the denoising task. Here we use a transformer based network to perform the denoising task. Compare our method with the state of the art methods. We use synthetic experiments and real experiments. For synthetic experiments, we to train the network weights, we use ImageNet images of 50,000 images. We test it on Kodak, BSD, and SET12 test images. For real experiments, we use SIDD medium training dataset and evaluate it on SIDD validation and test sets. The following diagram shows the qualitative comparisons of our method with the existing self-supervised denoising methods, where our method produces sharper and uh, clearer denoised images as shown in this second row and the third row. The following figure shows the qualitative comparisons of our proposed method with the state-of-the-art denoising methods, where our method SST-GP produces clearer and sharper denoised images as shown in the last column. The following table shows the quantitative comparisons on two different noise types, Gaussian noise and Poisson noise, where we can see our proposed SST-GP method outperforms the state-of-the-art denoising self-supervised methods. Following table shows the quantitative comparisons of our method against state-of-the-art methods on real-world noisy dataset called SIDD, where our SST-GP method outperforms the existing self-supervised noisy methods by significant margin in PSNR and SSIM as shown in this table. Thank you for attending our poster session.